Hello everyone and welcome back to a new video tutorial in Robot Structure Analysis Professional. In this video we are going to be discussing the modal analysis parameters as well as something called mass participation ratio. And before I start, of course, I want to mention that I'm going to start by having a model already done, and I want to give a shout out to Jorge Pedroso for providing me with this model that I will be using throughout this video. So here, of course, I'm assuming that you are well versed in Autodesk Robot. If you are not well versed in Autodesk Robot, I will be linking a playlist that talks about the entire basics of Autodesk Robot on the top right. With that being said, let's dive into the video. So sit back, relax, and enjoy the show. Alright, now before I start, I need to give a quick rundown of the model. It seems that the model here has a basement below the ground, and maybe there is an opening here for car ramps or something. Then you have here the ground floor, it seems, and you have here, of course, the roof. I can say also that this might be a staircase that is connecting this empty space. There's a staircase that connects the ground floor with the basement, and the base has been fixed, so it means that he might be going for a raft foundation, something that provides a fixation or a big support that actually provides fixation. Now for the load cases, there were multiple load cases. I deleted most of them because I want to focus on the model analysis today. You have the load case PP. Now I think this is Spanish. I don't know exactly what this means, but I can only guess. I think that this load case is the self-weight only, and you can see actually that he only has self-weight here. And you would think, wait a minute, why does he have a load case for self-weight only? And then the load case for dead load maybe, and another case for dead load, another case for dead load, and a case for live load. Why doesn't he, for example, put the self-weight in one of those dead loads? There is a reason behind that, and I will mention this later. This is actually a very good approach by him, and I will explain to you why this is the best way of making load cases if you want to make a modal analysis. So all in all, we have case number one, which is the self-weight, 3 cases which seem to be corresponding to dead loads, and 1 case which seems to correspond to live load. Okay, fantastic. Now, with that being said, we want to do a modal analysis. To do a modal analysis, you would have to go to something called analysis parameters by clicking on analysis and going to analysis types, which is strangely called here analysis parameters, but I mean, who am I to dislike those namings? If you click on that, then of course you see the typical analysis parameters that you can define and types. You can see here all the different load cases and the analysis type. You could change that if you want, but I'm not going to change it at all. I'm going to keep them, and now I'm going to define a modal analysis. But wait, before you define a modal analysis, you need to remember from your structures courses that a modal analysis means the solution of something called the eigenvalue problem. And the eigenvalue problem is a relationship between the stiffness and the mass. So in the eigenvalue problem, you have a stiffness and you have a mass. For the stiffness, that's easy. You have this stuff that will have a stiffness. For the mass, you would think, well, that's easy because, well, I can just take the mass of the structure. Well, here's the thing. Because some codes actually tell you exactly what to take. For example, do you take the entire dead load as the mass of the structure? Do you take part of the live load as a mass of the structure? This depends from code to code, and you have to double check your local codes. You have, before you define a modal analysis, you have to go to load to mass conversion. And you have to tell Robot what kind of loads are considered masses. You would think Robot can do this by himself. Well, no, he cannot. You have to tell him. And you can see that the current loads have been defined as masses as follows. 2, 3, and 4, which are the dead loads, it seems, have been defined as 1, meaning that I will take the full load of case number 2, for example, and I will consider it to be a mass. Case 3, I will consider it to be a mass. Case 4, I will consider it to be a mass. And case 5, I will consider it to be a mass, but wait, here is the thing. You can see that the coefficient is 0.2. So our dear subscriber Jorge is taking 20% of the live load, it seems, I'm only predicting here, to become his own mass. Now the 20% is something that changes from code to code and from region to region. You have to check your own code to see what the percentage is that you should take into account from the live loads. Like what percentage of live loads should be included in your modal analysis mass. Now, in case you're wondering how we can do this, well, let me show you. If we delete this, let me delete 5. So now I have 2, 3, 4 being added to the mass, and I want to re-add 5. The only thing I have to do is to write 5 here, or the load case, Or I can select it, basically. And the direction of the mass is, of course, downwards. It's going to be a global mass. And the coefficient is 0.2. I'm not going to change what our dear subscriber has defined. If you click Add, you can see now we are back in business, 5 at 0.2. And that's that. That's how you can add masses. Now, I know that you have a question. Wait a minute, CE. I thought that the self-weight is, well, as the word suggests, self-weight. So it should be a mass, right? Why wasn't the self-weight added here? You are expecting to put a 1 here for load case and 1 here for coefficient and add it. And you can see now the load case has been added. I'm going to delete it because no, I'm not going to do that. But why? Why am I ignoring the self-weight in the addition of masses to the structure? Isn't the self-weight a mass? Well, yes, and Robot does that for you. You don't need to put the self-weight here. Allow me to explain. If you go to Analysis Types now and click on New, you can define a modal case here. And if you click on OK, you get to the modal case parameters or modal analysis parameters. And it is here is the reason why we did not convert the self-weight. Because you can see that by default, the modal analysis will include the self-weight in its analysis, even if the self-weight case doesn't exist. Whenever you define a modal analysis, it will include the self-weight for you as a mass. And that's the reason why we don't include it here. Because if you include the case of the self-weight here and add it, then you would have double the self-weight. One of them is because you converted the self-weight into a mass, and another one is because the model itself takes the density and converts it into mass. Now you could do some convoluted shenanigans by disregarding the density here, and if you click on disregard density, then modal analysis will not add the self-weight, but then of course you have to yourself add the self-weight here. It's kind of convoluted, so my suggestion to you is always to add other cases, leave the self-weight alone, don't add it here, and just keep the analysis like this. Keep the modal analysis like this. Let's get into those parameters here. Today I'm going to explain everything related to modal analysis parameters here. Okay, now let's get into this. By the way, if you're wondering how I got this half, it's simplified parameters and advanced parameters. Let's start with simplified parameters. The number of modes is self-evident. It basically means the number of modes you want to calculate. I mean, you know what? Let me do a run for you. Just let me click on OK. Just a quick run to show you what this means. Click on OK. You can click on calculations here or calculations here. Both are the same. I click here, and you can see now the analysis is running, and I will explain to you what it means. Okay, now the analysis is complete. If you go to Modal here, you asked him for 10 modes, right? And if you click on mode here, you can see the 10 modes from 1 to 10. And yeah, you can just click, for example, on mode 1 and ask it to show you the deflection shape of mode 1. I clicked here, by the way, and you can see this is the deflection shape of mode 1. Now, we are still going to dive deeper, but wait for it. What I'm saying here is that since I asked for 10 modes, well, I got 10 modes. That's exactly what I got here. Now, what is this tolerance here? Well, if you go to advanced parameters, there are some iterative solutions. And let me go back to simplified. When Robot chooses to perform an iterative search, if you have studied the course numerical analysis in your BSc, you know that those iterative approaches will stop when you converge. And this tolerance means what is the error allowed for convergence. Now, a 0.0001 is a very, very, very small error. So let me rephrase that. This is the error, the approximate error that allows Robot to stop its iterations. It is basically the value of the current iteration minus the value of the previous iteration divided by the value of the previous iteration. If this is less or equal to 1 of 10,000 in this case, it will consider it to be convergent. And it's pretty small. I mean, I will let the editor show you an example. If we put 0.001, that's even very, very good and less accurate, but still very, very good. So, I mean, 0.001 is the error upon which the iterative search converges. The number of iterations is, as the name suggests, the number of times Robot tries to predict a certain mode. Of course, if it overshoots the 40, because it will keep trying to iterate until it reaches this error. If it doesn't reach the error during this number of iterations, you will get a warning from Robot telling you that the calculation has diverged. Now, it's pretty hard to make the calculation diverge, but it can happen nonetheless. For the mass matrix, there are three options. I am usually a fan of having a consistent mass matrix because, now, this is finite element deep, and I hope that you watched the finite element series. We are programming it also, that's another series. And when you calculate the stiffness matrix of an element, you are actually using the mode shapes in order to calculate the stiffness matrix. Now, mass matrix means that the mode shapes used in calculating the mass matrix are the same. They are consistent. They are the same as the mode shapes used for stiffness. Now, this usually means that it's a little bit more accurate, but you have more calculation effort to get there. Lumped is still okay. I mean, lumped is basically something that can get the job done, but I'm a fan of having consistent. Now, for the active mass directions, you can see X, Y, and Z are active. If you are interested in very, very detailed analysis, then you should have all three active. If only the horizontal movement is what concerns you, you can disregard Z and check out the horizontal movements. In my opinion, I like to have them all running because I want to see all the directions of vibration of the structure. Disregard density is what I said. We don't want to disregard density because I want robot to calculate the self-weight and add it. Storm check is a check by Autodesk that checks if a mode has been skipped, and it will recalculate it again. So this is what it seems to be the model analysis parameters. Now, our dear subscriber actually, shout out again to him, Jorge Pedroso. He emailed this because he has a problem called the mass participation. Now, this is strange. Allow me to explain. I'll just basically click OK here and run the analysis again, just for good measure. Okay, so the analysis is complete. And remember, I'm interested in the modal analysis today. Now, this is mode 1. If you click on the deflection shape, of course, you will see the deflection of mode 1. Now, let's give it a name. I will say that the mode number 1 seems to be the vibration around or in the direction of Y. You can see that the structure vibrates in the direction of Y. Now, this is me speaking. There is a way mathematically to verify that this is indeed in the direction of Y. But let's keep that for later. If we select mode 2 here, we can see that mode 2 is, it's loading, it is, let's see, it is movement in X, dominant, and some movement in Y, okay? Now, before I continue explaining, why does mode 1 look like this? Why is mode 1 in this certain direction? You need to understand what the frequency means, because those modes are sorted according to the frequency. The frequency is 5.9. If you go down, you can see the frequency is rising all the way up to 20 or something, or 15 at least in this case. We need to understand what those hertzes mean before I go any further. Let me explain this to you very simply. I'm going to use paint this time, just quickly check this out. If you have like a table, okay, a simple table, and you put on this table a ruler. You hold the ruler in place here with your hand, and you hit the ruler here, you tap the ruler with a finger. What happens with the ruler is, of course, it's going to vibrate up and down. This vibration is the frequency of vibration. It's the mode of the ruler. The ruler will be moving up and down, and this is the natural frequency of the ruler. The amount of times it goes up and down per second, that's the frequency. And here is the thing. The stiffer the ruler is, the faster its frequency. Think about it. If you take the same ruler, but let's say for the case of our explanation, you take the same ruler, but this time you put it further out. It's very free, you see. You hold it here, but the length that is free is more than our previous ruler. If you tap it again, the ruler will vibrate, but the vibration is going to be slower. Because when the ruler is longer, the stiffness is smaller, which will give you a smaller frequency. What I'm trying to say is, the smaller the stiffness, the smaller the frequency. And that's what happens here. Now, I didn't actually open the section so far for the structure, but immediately my prediction is that since the structure in the first mode is vibrating in the direction Y, my prediction is going to be that the columns are going to be weak around X because it will vibrate in Y, right? So you can actually open mode 2 and study it very quickly, let's try to describe them before I continue, because I promised you I want to show you some cool stuff. So let me show you. This is mode 2, and it seems that mode 2 is kind of twisty. I'm not really sure if I can call it twisty. It is in the X with a little y. Mode 3, let's take a look on that. Yeah, mode 3 is the torsion. You can call torsion. Let's see. And of course, torsion here means the inertia around the local X of the columns. You can see it's twisting. The entire story is twisting. Yeah, I think mode 2, I think I can call mode 2 the movement in X-ish, like mostly X with a little bit of Y. Okay, let's go to mode 4, for example, here. And let's see what this is. I don't know what this is. I cannot see it. Let me just check. Okay. Mode 4 is the vibration of the slab. Okay. Now, I will stop it here, but I want to show you something very, very interesting. If you go to Results, and then go to Advanced, and then go to Modal Analysis, you will see something called Mass Participation. Let me explain to you what those things are. Now, for mode 1, those 3 columns measure how much mode 1 vibrates in each direction. Allow me to explain. Mode 1, if you go back, vibrates dominantly in the Y direction, if you remember. Let me show it to you. Mode 1 vibrates dominantly in the Y direction. So what I'm trying to say is the mass of the structure is moving in the Y direction, okay? And because mode 1 moves the mass in the Y direction, if you go to the modal analysis results, you can see that indeed mode 1 moves around 43% of the mass in the direction of Y, okay? Now this is of course called the cumulative mass. That basically explains to you when an analysis ends, but at least let me talk about individual modes. This is for individual modes. This is for all modes so far. Like this here, those 3 columns are the cumulative of all the modes. Those 3 columns are mode specific. All right, now the next one is mode 2. And mode 2, I think we basically said it's kind of X-ish, and I stand corrected. It is really in X. Let me show you mode 2. Mode 2 is in X mostly. There is some movement in Y, but the main movement is in the X direction, and you can see this translated in the mass participation. You can see that mode 2 has a mass participation of 40% in the X. This mass participation helps you understand the modes. You know what? Let me make a bold prediction here. This mode is in the Y-axis. This mode is in the X-axis. This mode 3 is in neither axis. And because it's in neither axis, that's usually a telltale sign for a twist. This mode 4 seems to be in the Z-axis, it seems. So I'm predicting that mode 4 is going to be a little bit of torsion with a little bit of up and down movement. You can see mode 5 and 6 is predominantly in Z. So I'm predicting that those 2 modes are going to be for the slabs. And now here, I kind of lose the prediction abilities because you can see this is 1%, not really much. But at least, let's see if we were able to predict those first 6 using the mass participation. Remember, first one is Y, second one is X, third one is twisting, fourth one might be twisting plus up and down movement, fifth and sixth are up and down movement. Let's take a look to those. I'll go to view and see. Well, mode 1 was movement in Y. Fantastic. Mode 1 was movement in Y. Mode 2 was movement in X. I mean, we use the mass participation in predicting the movements. Okay? Now, mode 3 is twisting because there was no movement. And you can see, yes, it is twisting. Now, I would think, wait a minute. I mean, obviously, masses are moving. Yes, but the center of gravity is not really moving. What I'm saying is, there are movements of masses to the right, and there are movements of masses to the left. They kind of cancel each other out in a twist. But here, everything is moving to the right. So here, there is no cancellation of movement. This is much different than this, and that's why you have little mass movement. I know that individual masses are moving. This mass, for example, is definitely moving. But all in all, there are things move right, there are things moving left, so they kind of cancel each other out. Let me remember what we were doing. I think, okay, 4 was in the Z a little bit. 5 and 6 are predominantly in Z. So let's take a look how this translates into the modes. Let's take a look on 4. Okay, yeah, 4, you see, it was a little bit in Z. So you can see. Now, don't be freaked out by the sheer hugeness of the movement. Mode shapes do not have values in meters. They are normalized values. So this value is just for show. It doesn't mean that it's big or small. It's normalized. And you can see that the slab is indeed moving up and down, and that's why you have something in Z. Going on to mode 5, there is a massive increase in Z, so something big must happen in mode 5. I don't know what happens here. Really? Well, that's strange. I thought I'm going to see something more. Oh, wait. Yeah. I think I know why. Look, in mode 4, there are masses moving up and masses moving down, and you can see that maybe, because I told you it's a summation, right? Like the stuff is going up, stuff is going down. Basically, they kind of cancel each other out, at least in the calculation perspective. Now, the mass is moving, don't mind me. The mass is moving, I know that, but they kind of like the upward movement and the downward movement are the same. But if you go to mode 5, I guess, then everything is moving down. This is moving down, that is moving down, that is moving down. The entire structure, even here, you cannot see it, but this part is moving down. You can see it maybe in 3D. Yeah, there we go. So you can see that the entire structure is moving down, and that's why the mass participation is higher, because there is no cancellation. Let's see mode 6. Mode 6. Yeah, mode 6. Wait, there is something cancelling up, right? Wait, let me check something here on dynamic. Mode 6, 13%? Well, this is strange. Let me try and understand this. So mode 6 has this, and this bulging down, this bulging up. Maybe the summation of the downs are much higher than the summation of the downs here. I mean, if you go here in 5. Yeah, I think that's the case. Like this bulge plus this small bulge plus this small bulge is a little bit less than all those things bulging down and this going up, it seems. Okay, mode 7. Yeah, mode 7 is kind of cancelling each other out. It's still in Z. By the way, everything is in Z, it seems. That's kind of interesting. It seems the structure is not easy to vibrate in X. Okay, mode 8. I'm just gonna cycle through the modes now. It's still the slab. Mode 9 is still the slab, I guess. Mode 10 is, I think, still the slab. Yeah, okay. So the slab seems to be vibrating in modes 5 up to 10 or something. Now here's the kicker. The problem with this modal analysis, and that's the reason why Jorge sent me this, is because the mass participation is too low. Allow me to explain this. The problem with the analysis is that the entire mass is not moving. Like, he has done 10 modes and he was only able to get cumulatively around less than 50% of the mass to move. Now, why is that? We need to understand, first of all, why this is and what we can do about it. The reason why this is because indeed the mass is not moving. What do I mean by this? I mean by this that those shear walls never moved. If you go to mode 1, they are not moving. If you go to mode 2, they are not moving. So the modes we have here, even if you go to 3, 4, if we cycle through all the modes, those shear walls were never able to move. And because of that, the mass participation is low. I mean, this even makes sense. Look, in mode 1, let me show you something. In mode 1, it is the top slab that is moving, and the bottom slab is basically not moving. You can predict and say that around half the structure is moving and the other half is not moving. Now, this is totally normal because you have a shear wall, or you have a wall which is a stiff element. And because half of the structure is moving, in the dynamic analysis you can see that indeed 43% of the structure is moving. This is exactly what it's supposed to be. This is perfectly fine. Now, let's say we want to ask the question, first of all, what is an acceptable cumulative mass participation? Now, I tried, and I really recently tried that. I tried looking up resources or references And at least in the course that I am aware of, I didn't find a certain guideline for relative mass participation. I didn't find that, unfortunately. If you have something, then please share it with me. I only found rules of thumb which say that the mass participation, and even Autodesk says this, I only found rules of thumb, and even Autodesk doesn't have in its website a clear indication. It just tells you, well, it should be more than 80%. So I only found rules of thumb that basically say that it should be over 80%. And even I had some discussions with professionals with that regard, and I think we both agreed. But of course, that's not the answer. Let's say that we are interested into making the mass participation happen. To make the mass participation happen, I must let the structure vibrate here. This story must vibrate. Those shear walls or those retaining walls must vibrate. Now, notice this. Because the retaining walls are very stiff, they are going to have a very high frequency. So we are going to reach huge numbers of modes before we are able to vibrate those things. And to do this, let's go to Modal again and discuss the parameters once again. In the parameters, you can click on Advanced Parameters, and this is where the things become interesting. Now, our analysis is going to be Modal, of course, and our method here, I will keep it subspace iteration. You could use the Lanczos algorithm. Those are algorithms that are mathematical methods, and I am a fan of Lanczos, by the way, but I will keep it for subspace for now, despite the fact I am really a fan of Lanczos algorithm. You can check out the documentation of those methods on Autodesk's website. So this is a mathematical thing. The damping here is 5%. That's okay. You could change it. Now you need to refer to references when you want to change the damping. If you have a steel structure, then the damping is going to be a little bit low. It's going to be like between 1 to 10%. Please check references for that. If you have concrete structures, the damping might be higher. Now relax. The difference between an undamped and a damped frequency is not going to be that much. You can check out the dynamic books for this. Of course, I'm talking about damping in the normal regions, not damping like super damped or like 50% damping. I'm talking about the regular ranges of damping. The regular ranges of damping for steel structures is not going to have an effect on modes. For concrete structure, it may have an effect. So please check out your references for more. I'm going to keep it 5% here. So it seems that those advanced parameters do nothing. Well, no, they actually do something, and we're going to access this % of mass participation later. You could actually click on it and put here a value. But before I click on it and put a value, let me explain to you what you will find. So we are going to change this in a moment. But before we change this, let me tell you what you will find if you Google how to increase mass participation in modal analysis. If you Google how to increase relative mass participation in Google, you will find the answer that is, well, increase the number of nodes. Now, why is this the answer you will find? It's because we have just explained it. The mass that is vibrating here is only 50% of the structure. Why? Because the lower part is much, much stiffer, which means we need higher modes, because stiff equals more frequency equals higher modes. So let me try something here. Let me put 30. Now remember, let me just first of all remind you, our total mass participation was around 40-ish% and 30-ish%. Let's just increase it now to the parameters and increase this to 30, okay? And hit the OK button and then calculate. Okay, so the analysis is complete and you have now 30 modes at your disposal, but let me go quickly to the dynamic analysis and see. You can see suddenly that the relative mass UI, there is an improvement, right? You can see that we were here and now we are here and the relative mass has improved. And I can see something strange. Like, let's take a look between 10 and 30. At 10, it was 42-43, and at 30, it was 44 and 86. There is a sudden jump in UI. Let's take a look where this jump happened. Let's see. Here it is. Here, there is a jump in UI. I think that's the second mode of the structure in Y. This is mode 24. Let's take a look how this sudden jump translates in the modal analysis. You can notice that the rest of this stuff is just in Z. So I'm predicting that all of those things are the vibration of the structure slab. But this is interesting. Let's go dive into it and check it out. It's mode 24, so I'll go to view and I will select mode 24 and take a look exactly how it looks. So mode 24 selected, it's in Y, so let's see what happened. Ah, there it is. Look at this beautiful movement. You can see that finally, we were able to move the shear walls or the retaining walls. And that's the reason why you have suddenly some extra 40% moving. I know that the slab seems to be stationary, but the shear walls have a net movement in Y, and that's why suddenly you have a spike in the Y direction with yet another 40%. So you can see how increasing the modes actually improves the outcomes of the analysis. Keep trying trial-error games until we reach a certain mass participation. Let me say that I am targeting 85% mass participation. Allow me to show you. If you go to view and then basically click on parameters here on the model, here in the advanced, I told you we're going to play with this, the calculation when you reach a certain frequency or when you reach a certain mass participation. That is what I need. Let me put 85% here. I'm not changing the number of modes. And if I click on 85% here, before I click OK, let me run down very quickly here. The damping here is for the structural damping. The include damping calculation, I think this is based on the foundation damping. Check that out. Eccentricity are extra eccentricities you want to define for the center of mass. I don't want it. So what I'm very interested in, you can basically narrow it down to this. This is one of the most important things you will have to play with if you are targeting a certain percentage of mass participation. Let's put one mode now. We know that one mode will never reach this mass participation. But let me put one mode, hit OK, and calculate, and show you what Robot tells you. Okay, now the analysis is complete. There is a bogus instability that has been introduced. I will have to remove it very quickly. But you can see that Robot warns you and tells you the participation of masses is not satisfactory. Why? Because you asked him for a certain limitation of 85%, but you only did one mode. So let's increase that. Okay, so you saw the error in action, and that's a good thing, by the way, to keep the present of mass participation 85%. Robot will warn you if this mass participation hasn't been reached. That's a good way because sometimes you can forget checking that, so that's a good way of keeping this in your calculation. Now let me increase the number of modes. Let's say, I don't know, 50. I hope 50 will do the trick. And let me remind you, the reason why this works is because we are trying to excite the basement, which is pretty hard to excite. And later I will tell you my thoughts about this. But for now, let me first of all try to achieve this 85% by clicking OK here and performing my calculation. Okay, so I have news for you. I still wasn't able with the 50 nodes to get the mass participation up to 85%. We're getting close. I'm kind of annoyed, to be honest. I will mention what this means in a moment, but for now let me try again and change. Let me change very quickly to more modes. I have a lot to say at the end of this video, but for now, let me just try to achieve the 85%. Now, by the way, it's warning me because I have the warning here running. I will just click OK here and I'll try it again. So now we are at 100. Okay, the participation of masses is still not enough, but I think I will stop. But you can, let's see first of all before I stop and decide to stop. Let's see, at the 100th node, I have X achieved, Y achieved, but Z not achieved. So you can see that you still need to increase the number of modes to achieve this mass participation on paper. Now, before I give you my thoughts, because I have a lot to say about mass participation, I want to quickly check out something. I want to check the jumps. So we checked mode 24, which moved the basement wall. Remember that? We checked it here, mode 24. It has a sudden spike in mass participation UI. And you can see that the basement wall finally moved in mode number 24. I also want to check the next movement in the X. So you can see here and here. There are two movements happening here. One of them is at 37.99, one of them is at 38.55. Let's take a look at those two. And even here, it seems that there are three nodes. It seems there are three modes that are kind of very close to each other. They might be giving the same movement. I don't know. Let's take a look. So 32, 33, and 34. Let's go to view again. 32 has something in X, but why? Let me see. Where's the X movement here? Really? That little bulging? Well, it was just 5% after all. Maybe here. Yeah, I think this one. This one is moving in X. You can see it's de-aligned. But that's not much, and it's just 5%. Let's go to 33. There was a sudden spike there, and I'm expecting a lot of movement in X here. So let's take a look on it. You can see the bulge is larger. Did the shear wall move? Or the retaining wall? Yes, the retaining wall started moving. Yes. You can see the retaining walls now, finally, because they are very stiff at 38 Hertz, they start moving in the X direction. That's why suddenly the X has more mass participation. And yeah, okay, so you can get the idea of mass participation. Now, what are my thoughts about mass participation? My thoughts are very simple. Mass participation is not a holy Bible. You can see that we have sudden spikes in mass participation in mode 24 and mode 33. Let me go to mode 24, for example. Mode 24 has a frequency of 31.2 Hertz. That's a lot, by the way. I mean, rotating machinery, like sieves or crushers, might have a frequency in the ballpark of 10s and 20s, not 31s. So, yes, the structure can vibrate like this. That is true. But the question is, what kind of force would have a frequency, what kind of significant force would have a frequency of 31.2 Hertz? Okay, you could still defend this, but what about this node, 34? This mode, 34. Look at this. This is in the ballpark of the 40s, I think. Let me check. Yeah, we are now in 40 Hertz. Now, it becomes harder and harder to move structures like this. What I'm saying here is, you just cannot simply force a certain mass participation because sometimes the mass just doesn't participate. It doesn't participate because for all means and purposes, going to the 33rd mode at 40 Hertz is interesting, yes, but is there really a force that can excite the structure in that frequency? Well, you can even go crazier and go all the way up to 600 modes, and then you would get your final mass participation, which is cool on paper, but does it really matter? That's the question I want to include before I finish, and still there's another thing. There is another thing that is missing in this model. You see, I think, if I understood correctly, I think that this is a basement underground. And if you have a basement underground, the walls cannot vibrate freely. This is not true. This is not accurate. Like, let me show you mode 24. Mode 24 is not accurate. You can see the retaining wall if this is underground. You can see the walls are moving, but in reality, this wall is retained by soil, and this wall may be retained by soil. So I think even the model analysis here might not truly reflect the structure on the field, because, I mean, the retaining walls underground might not be prone to vibrating because they are held in place by the ground itself. You could add some springs here, just check out how they will affect if you want to model the soil with springs, but make sure that those springs are only compressive springs. So when you add them, they are only active if you compress against them, because soil cannot pull, it can only push. It cannot pull the structure back in place. So what I'm saying is, yes, the idea of mass participation may be interesting, but sometimes it just doesn't make sense. What I suggest here is to not include the retaining wall masses in your analysis, because I don't think they are vibrating. This is high-level stuff. I need to sit down and research it myself, but at least I want to tell you this. Those walls underground would not vibrate like this, and the entire structure underground, you could make the mass participation reach 80%, but it's kind of superficial. You are going up to frequencies of 40 and 50 and 60 Hertz and whatnot, and it becomes kind of unfeasible to vibrate the structure like this, because why do we do a model analysis? We do a model analysis because we want to check if there are, for example, resonances, if we want to use the modal decomposition, and it kind of makes it harder and harder to vibrate structures at those frequencies. So, I don't know how to say this, but I would be very satisfied with 80%, and that's it, and just leave it like that. Furthermore, it seems, and this is the third time I see this in action, it seems that the structures are harder to vibrate in Z. The reason why they are harder to vibrate in Z is because the axial, like look, why would a structure vibrate in Z? A structure would vibrate in Z if the slab vibrates or the walls vibrate. Now the slab vibrating in the Z means bending of slab, and the stiffness of bending can be vibrated. However, other things are also related to vibration in Z are the axial stiffness of those walls. And there is no way you can vibrate those walls in the Z axis. They are just too stiff. You would reach mode 600 and you are still not able to vibrate those walls in the Z axis. Now I hope this sheds more light, a little bit more interesting aspects of the model analysis. I hope that you now by this video become model analysis masters. Feel free to comment in the comment section if you have questions. I would be more than happy to answer them. And before I finish, I want to give a shout out to engineer Jorge Pedroso, who allowed me to use this robot model for this video. And of course, I want to give a mass participation sized shout out to my dear channel members in the contributor level and the helper level, whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support to the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing and commenting, especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel and we will catch you in the next video. Bye bye.